Welcome back to part 2 of the second lecture for chapter 11, Organometallic Compounds. We were just talking about examples of the metathesis reaction. Here are two more examples. In the top example, two different alkenes can be used as the starting materials for metathesis. And you'll notice here we got two alkenes. This molecule on the left has 1, 2, 3, 4 carbons. This one has 1, 2, 3, 4, 5, 6. So we got 4 plus 6 forming two molecules of a new alkene product that has 1, 2, 3, 4, 5, so a total of 10 carbons. Of course, we have reactants that are smaller, 4 carbon, 6 carbon, and they're going to form two 5 carbon, total of 10. But each one of them is 5 carbons. The second example, in the bottom, you can see alkynes can also undergo metathesis reactions. The preferred catalysts for alkyne metathesis are called Schrock catalysts. These are catalysts that contain molybdenum or tungsten as the transition metal. And over on this side, you should put a 2 right in front of this molecule. There's 1, 2, 3, 4 carbons in that alkyne, forming these two different products, the two ethenes, and notice two alkenes, and notice this one is ethene, but 1, 2, 3, 4, 5, 6, and 2, 6 plus 2 is 8. Two of these, two 4 carbon reactants represent 8 carbons. So we still have alkene products being formed. Let's go to the next slide. Okay, now we have a series of review questions and problems that will help you review the material from chapter 11. The first one you can see here, it says, which of the following solvents is or are suitable for the preparation of a Grignard reagent? Just looking down this list, hexane, tetrahydrofuran, ethanol, ethyl ether. You may remember when we were discussing the Grignard reagent, it requires a polar aprotic coordinating solvent, such as an ether. And really just from memory, learning the overall reaction, you'll remember tetrahydrofuran, THF, and ethyl ether are the solvents that are suitable for the Grignard reagent, as indicated on this next slide. So B and D are the correct answers. Here's the next problem. You may want to pause for a moment and think about this before going right on to the answer. But what is the product of the following reaction? So take a look at that for a minute. You might notice, looking at this, it's a two-step process. Magnesium and THF, tetrahydrofuran, are very reminiscent of a particular type of reagent, which you're probably thinking of, the Grignard reagent. We're going to form the Grignard reagent, which is nucleophilic. We'll take the bromine off and put magnesium between the bromine and the carbon. So now we have magnesium bromide as a substituent on this cyclic structure right there. That is what occurs in the first step, number 1. Then secondly, this is very nucleophilic. This carbon right here is nucleophilic with magnesium bromide present. And water molecule, of course, is made up of a hydrogen cation and a OH anion, or hydroxide anion. So the nucleophile is going to go for one of the protons, and as a result, the magnesium bromide substituent is replaced by hydrogen. So just looking at A, B, C, D, and E possible answers, you can see D has the hydrogen attached to that carbon in the place of bromine. So D is the correct answer. And as noted on this slide, the Grignard reagent, which provides a nucleophilic site represented by magnesium bromide bonded to an R group, which in this case is this cyclic alkene, or a carbon, which is this carbon right here, forms first, which then reacts with a proton from the water molecule, which is electrophilic. The proton is. This is formally a reduction reaction, in that we're creating more carbon-hydrogen bonds, and THF is only a solvent. So as you know, THF is not going to participate in the reaction. Okay, let's go to the next slide, and again, take a look at it. See what you think the answer is before proceeding. What is the major product of this reaction? So take a look at it. Again, this one also is a two-step process. And looking at this, we see we already have a Grignard reagent right here as a reactant because of the magnesium bromide. So we would expect this to be a very nucleophilic carbon. And we've got an epoxide containing molecule here. That carbon and this carbon in the ring are certainly good electrophilic sites, but we'll notice that the carbon here on the left is less hindered than this carbon on the right because it has a methyl group attached to it. So this carbon is going to be a better electrophilic site for the nucleophilic carbon in the Grignard reagent. So it's going to come around and try to make a bond with this carbon. As a result, these electrons between this carbon and oxygen are going to come upon the oxygen atom, breaking this bond, and now we have formed a new structure where we've taken this 1, 2, 3 carbon chain, and it is now going to be bonded to this carbon, which let's call that number 4, and then this oxygen bond right here breaks. Oxygen remains bonded to carbon number 5, and this is number 6 in the new product. Then notice to see the second step is a hydronium ion, which is water molecule and a proton cation. And of course, with the oxygen with the negative charge, the proton is going to relieve that positive charge, bond to it, forming an OH moiety on or in this compound. So if we call this 1, 2, 3, 4, 5, 6, the OH is going to be on number 5. So looking at the possible selections, here this is 6, 5, 4, so OH is in the wrong place. Here it's on number 6 if we count it 1, 2, 3, 4, 5. It's actually number 5 right there. Then we look at this compound. Looks like it's in the right place because we've got this 1, 2, 3, 1, 2, 3. And then this carbon is this one right here, and the OH is bonded to number 5. So it looks like C should be the right answer. Nucleophilic ring opening of the epoxides occurs at the least hindered carbon, again because there is no methyl group. It has 2 protons bonded to it, but not a methyl group and a proton. And again, the second step relieves the negative charge that's on the oxygen after this bond breaks and the electrons go onto the oxygen. Okay, let's continue on. Here is another question. The following reaction is an example of a blank reaction. So we need to pick which of these. We got all of the coupling reactions plus the Grignard reagent reaction that's listed here. So let's look at this. Which one do you think it is based on what we've got? We've got 2 reactants present. One of them's got a boron containing moiety, and we got a palladium catalyst. And looking back at the mechanisms, the overall reactions, you remember that the Heck reaction, Still reaction, Suzuki reaction all have palladium-related catalysts. Heck has an alkene, Still has a steinane type moiety, and Suzuki is the one with the organoborane. And there is an organoborane component here and palladium. So it looks like most likely the answer should be Suzuki reaction. And yes, it is. The Suzuki reaction is based upon reaction of organoborane compounds with alkenyl and aryl electrophiles, as we can see here. Let's go to the next one. What type of reaction could not be used to accomplish this reaction displayed here? What type of reaction? Gilman, Grignard, Heck, Suzuki, all of these will work. So which would not be used? Take a look at that for a minute. And as you look at this, you realize that this carbon is an electrophilic site as the bromine departs. The Gilman, the Heck, the Suzuki reactions always couple in a real benzyl or vinyl halide with its particular reagent. The halogen, in this case bromine, is the leaving group. With Grignard reagent, it reacts with another electrophilic carbon. The Grignard reagent has the leaving group, or the magnesium bromine departs. So it looks like the exception, the type of reaction that would not be used to accomplish this, would be B. Grignard reagent would react with the carbonyl group, not the halide, most likely. But Gilman, Heck, and Suzuki, again, reactions always couple in a real benzyl or vinyl halide with a particular reagent. And the halogen is the leaving group. Okay, here we go. Name the following reaction type. Okay, this is our last question, our last problem, practice problem. So take a look at this for a minute before we get to the answer. Okay, taking a look at this, you'll see we didn't write it in here, but if you notice, we form a bond between these two, we are going to lose a 2-carbon component of this molecule, which will be ethene. An ethene product tells us that it must be a metathesis reaction. Gilman, Gilbert, Heck, Suzuki, and so forth would not form this kind of product, but having ethene tells us that it must be metathesis, Grubbs/metathesis reaction. So the loss of an alkene to form the product is indicative of metathesis. Okay, that concludes our discussion of organometallic compounds. Chapter 11 is finished.